In this section, I'm going to discuss the unilateral Laplace transform. Although the unilateral Laplace transform was introduced very briefly at the beginning of this unit on the Laplace transform, so far we focused our attention exclusively on the bilateral Laplace transform. At this point, I'm going to consider the unilateral Laplace transform in more detail. This coverage of the unilateral Laplace transform will be mainly geared towards the application of solving differential equations. At the beginning of this unit on the Laplace transform, we were told that two versions of the Laplace transform are commonly used, namely the bilateral and unilateral Laplace transforms. Then we proceeded to focus our attention exclusively on the bilateral case. At this point, I'd like to formally introduce the unilateral Laplace transform. The unilateral Laplace transform of the function little x, which is denoted by script L subscript u little x, or simply big X, is given by this particular formula here. Observe that the integral that defines the unilateral Laplace transform, in other words this integral here, is identical to the integral that defines the bilateral Laplace transform, except for this lower limit of integration, which in the case of the unilateral Laplace transform is 0, and in the case of the bilateral Laplace transform is negative infinity. Although the unilateral and bilateral Laplace transforms are distinct transforms, a very simple relationship exists between them. In particular, the unilateral Laplace transform of the function little x is simply the bilateral Laplace transform of the product of little x and the unit step function. A proof of this relationship is given here. Let's examine this proof in more detail. The unilateral Laplace transform of the function little x is given by this particular equation here that's highlighted. Next, we can observe that this integral can be rewritten in terms of the next integral by using a unit step function and changing the limits of integration. Next, we can observe that this highlighted integral is simply the bilateral Laplace transform of the function little x times the unit step function. In other words, we have this result here. Since the unilateral Laplace transform of little x is equal to the bilateral Laplace transform of little x times the unit step function, and little x times the unit step function is always a right-sided function, the region of convergence associated with the unilateral Laplace transform of little x is always either a right half plane or the entire complex plane. In other words, the algebraic expression of a unilateral Laplace transform unambiguously determines its region of convergence. For this reason, we don't usually specify the region of convergence explicitly when working with the unilateral Laplace transform. The region of convergence is simply understood to be the one that corresponds to a right-sided function. The unilateral Laplace transform uses the same formula for inversion as the bilateral case. Unlike the bilateral Laplace transform, however, the unilateral Laplace transform is only invertible if we restrict the functions for which we take the Laplace transform to be causal. This follows from the fact that the formula for the unilateral Laplace transform of a function little x does not depend on the value of little x of t for t less than 0. In effect, taking the unilateral Laplace transform of a function little x discards all information about the value of little x of t for t less than 0. As long as the function little x is causal, the unilateral Laplace transform of little x can be inverted to obtain little x once again. A proof of this fact is given here. Let's examine this proof in more detail. To begin, we have an expression that corresponds to taking the unilateral Laplace transform of little x and then immediately taking the inverse unilateral Laplace transform of the result. First, we can observe that the unilateral Laplace transform of little x can be rewritten as the bilateral Laplace transform of little x times the unit step function. Next, we can observe that the inverse unilateral Laplace transform is the same as the inverse bilateral Laplace transform. So we can rewrite this highlighted expression here as this expression here. Next, we can observe that the bilateral Laplace transform is invertible, so these two operations here will cancel, and what we're left with is just the function little x times the unit step function, which is equivalent to this formula here. Now observe that this result is equal to little x as long as little x is causal. From the preceding proof, we can see that the inverse unilateral Laplace transform always yields a function that's causal. Since the unilateral Laplace transform effectively discards all information about a function little x at points less than 0, the unilateral Laplace transform is typically only used in situations where either the function little x is causal, or we simply don't care about the value of little x of t for t less than 0. Due to the close relationship between the unilateral and bilateral Laplace transforms, these two transforms have many similarities in their properties. Since these two transforms are not identical, however, their properties differ in some cases. At this point, I'd like to quickly highlight some of the key differences in the properties of the unilateral and bilateral Laplace transforms. In the case of the unilateral Laplace transform, we have the following key differences. Firstly, the time-domain convolution property has the additional requirement that the functions being convolved must be causal. Secondly, the time-domain scaling property has the additional constraint that the scaling factor must be positive. Thirdly, the time-domain differentiation property has an extra term in the expression for the unilateral Laplace transform of the derivative of little x. Namely, we have an extra term of this particular form here. Fourthly, the time-domain integration property has a different lower limit in the time-domain integral, namely a lower limit of 0 instead of a lower limit of minus infinity. And lastly, the time-domain shifting property doesn't hold, except in special circumstances. In the context of this course, we're primarily interested in the unilateral Laplace transform as a tool for solving differential and integral-differential equations, in other words, equations involving derivatives and integrals. For this reason, the unilateral Laplace transform properties of most interest are the time-domain differentiation and time-domain integration properties, as well as the linearity property. So of the differences between the unilateral and bilateral Laplace transforms listed on this slide, items 3 and 4 are the most important, as they relate to differentiation and integration. This slide summarizes the key properties of the unilateral Laplace transform in table form. Unlike in the case of the bilateral Laplace transform, a table of properties for the unilateral Laplace transform does not need to provide information about the region of convergence. This is due to the fact that the region of convergence of a unilateral Laplace transform must always be the one that corresponds to a right-sided function. Since the region of convergence is always implicitly known, there's no need for the table to provide information about the region of convergence. Again, in this course, our primary interest in the unilateral Laplace transform is as a tool for solving differential or integral-differential equations. Therefore, of the properties listed on this slide, the most important ones are the time-domain differentiation and time-domain integration properties, as well as the linearity property, all of which are marked by asterisks. In the case of the time-domain differentiation property, the Laplace domain expression for the unilateral Laplace transform has an extra term relative to the bilateral Laplace transform. In particular, we have this extra term here. In the case of the time-domain integration property, the time-domain expression for the unilateral Laplace transform has a different lower limit of integration relative to the bilateral Laplace transform. In particular, we have a lower limit of 0 instead of a lower limit of minus infinity. When solving problems using the unilateral Laplace transform, we'll often find ourselves needing to compute the forward or inverse unilateral Laplace transform of certain commonly occurring functions. To assist with such computations, we often rely on a table of unilateral Laplace transform pairs. An example of such a table is shown on this slide. Unlike in the case of the bilateral Laplace transform, a table of transform pairs for the unilateral Laplace transform doesn't need to provide information about the region of convergence. This is due to the fact that the region of convergence of a unilateral Laplace transform must always be the one that corresponds to a right-sided function. Since the region of convergence is always implicitly known, there's no need for the table to provide information about the region of convergence. Furthermore, since the unilateral Laplace transform is only invertible if we restrict the functions for which we take the Laplace transform to be causal, this table ignores little x of t for t less than 0, simply assuming that little x is causal. Many systems of interest in engineering applications can be characterized by differential or integro-differential equations, in other words, equations involving derivatives and integrals. One particularly important class of equations is constant coefficient linear differential equations. Often the unilateral Laplace transform is used to solve such equations, especially when the solution to be found must satisfy certain non-zero initial conditions. Although the bilateral Laplace transform can also be used for solving differential equations, it can only effectively handle equations for which the initial conditions are all zero. In practice, however, initial conditions are often non-zero. For this reason, the unilateral Laplace transform is usually more useful than its bilateral counterpart for solving differential equations. At this point, I'd like to consider a couple of examples that relate to using the unilateral Laplace transform to solve differential equations. First, I'd like to consider example 7.42. In this example, we're asked to find the unilateral Laplace transform big Y of the function little y in terms of the unilateral Laplace transform big X of the function little x, where little y and little x are related by this particular equation here, and the prime symbol denotes derivative. In being asked to find big Y, we're effectively being asked to take the unilateral Laplace transform of the given equation, in other words, this particular equation here. Since this equation contains a second-order derivative, in order to take the unilateral Laplace transform of this equation, we need to apply the differentiation property of the unilateral Laplace transform twice. To reduce the likelihood of making a mistake, we're going to split the solution into two steps, where each step involves only applying the differentiation property once. To this end, we rewrite the given equation as the pair of equations 7.17 and 7.18, in other words, these two equations here. Now we'll proceed to take the unilateral Laplace transform of each of these equations and then use the results obtained in order to find big Y. First, let's consider the unilateral Laplace transform of equation 7.17, in other words, this equation here. Taking the unilateral Laplace transform of this equation trivially yields this line here. At this point, we need to simplify this unilateral Laplace transform, and we can do this using the time domain differentiation property of the unilateral Laplace transform. Doing this gives us this next line here. Next, let's consider the unilateral Laplace transform of equation 7.18, in other words, this equation here. Taking the unilateral Laplace transform of this equation trivially yields this line here, where we now need to simplify this unilateral Laplace transform expression. Using the time domain differentiation property, we can do this to obtain this particular result here. Now substituting equation 7.19, in other words this equation here, into equation 7.20, in other words this equation here, yields this next line here. Multiplying s into the factor in square brackets and using the fact that little v is equal to little x prime, we obtain this next line here. So in conclusion, we have that big Y is given by this particular formula here. Next, I'd like to consider example 7.43. In this example, we're given a causal incrementally linear time-invariant system with input little x and output little y that's characterized by this particular differential equation here, where the prime symbol denotes derivative. Furthermore, we're told that the input to the system little x is given by this formula here, and the output of the system little y satisfies these initial conditions here. Then we're asked to find little y. To solve the given differential equation, we're going to use the unilateral Laplace transform So to begin, we need to take the unilateral Laplace transform of the given differential equation. In other words, this equation here. Taking the unilateral Laplace transform of this equation, we trivially obtain this next line here. Next, we're going to use the linearity property of the unilateral Laplace transform to split this unilateral Laplace transform calculation into three separate unilateral Laplace transform calculations. This yields this next line here. Now we essentially have two non-trivial unilateral Laplace transform calculations to make. This first one here is going to involve the differentiation property of the unilateral Laplace transform, and this second one here will also involve this property. So using the differentiation property of the unilateral Laplace transform, we obtain this next line here. Next, we can multiply the 3 into the terms in square brackets to yield the next line, in other words, this line here. Now we move the terms not containing big Y to the right-hand side of the equation and factor out big Y on the left-hand side of the equation. This yields the next line, in other words, this line here. Then we can divide both sides of the equation by s squared plus 3s plus 2, in other words, by this factor here that's written in the annotation. And by doing this, we obtain that big Y is given by this particular formula here. Next, we're going to find the unilateral Laplace transform big X of little x, where little x was specified in the problem statement and is given by this particular equation here, which is labeled as equation number 3. Taking the unilateral Laplace transform of this equation, we obtain this equation here, where we now need to simplify this unilateral Laplace transform expression. To do this, we can simply look up the answer in our table, which yields this result here. Now, substituting the expression that we just computed for big X and the given initial conditions for little y into this equation here yields this next line here. At this point, we now need to take the inverse Laplace transform of big Y. To do this, we're going to use a partial fraction expansion. So we can observe from this expression here for big Y that the function big Y has three poles, a pole at 0, a pole at -1, and a pole at -2, where all of these poles are simple poles. Therefore, the partial fraction expansion of big Y will have three terms, one term contributed by each pole. In particular, the pole at 0 contributes this term, and the pole at -1 contributes this term, and the pole at -2 contributes this term. So now we need to compute the partial fraction expansion coefficients a1, a2, and a3. First, we compute the coefficient a1. This coefficient is associated with the simple pole. Therefore, we use the formula for computing a partial fraction expansion coefficient that's associated with the simple pole. Doing this and grinding through the arithmetic, we obtain a value of 5/2. At this point, I'm going to pause in order to scroll the example upwards so we can see the remainder of the solution. Now we continue from where we left off, proceeding to compute the coefficient a2. This coefficient is associated with the simple pole, so we compute this coefficient using the formula for a partial fraction expansion coefficient associated with the simple pole. This results in a value of -4 for this particular coefficient. Lastly, we compute the coefficient a3. This coefficient is also associated with the simple pole. Therefore, we compute this coefficient using the formula for a partial fraction expansion coefficient associated with the simple pole. This results in a value of 5/2 for this particular coefficient. Substituting the values computed for a1, a2, and a3 into the partial fraction expansion for big Y yields this particular partial fraction expansion here. Now we proceed to take the inverse unilateral Laplace transform of big Y. Taking the inverse unilateral Laplace transform of big Y with the help of the linearity property, we obtain this line here, where we now have three inverse unilateral Laplace transforms to compute. Each of these inverse unilateral Laplace transforms can be computed by using a table. The first inverse unilateral Laplace transform, in other words this one here, can be computed by using this particular pair in the annotation, which is taken from our table. The second inverse unilateral Laplace transform, in other words this one here, can be computed using this particular pair taken from our table. The third inverse unilateral Laplace transform, in other words this one here, can also be computed using this same pair taken from our table. Using these unilateral Laplace transform pairs taken from our table, we obtain this particular result here for the inverse Laplace transform of big Y, in other words for the function little y.